Hello everyone, welcome back to our engineering mechanics dynamics class. Today we're going to solve some one relative motion example. And for the relative motion, we're going to use two planes that are moving relative to each other, and we're going to find what a velocity and acceleration of one plane with respect to another. So let's see. Our learning objective is to solve a relative motion problem that has a translating axis problem. In this example, we'll apply the concept of relative motion of two particles that we have derived in our previous classes, which is kind of simple in vector rule. And we're gonna apply that concept to determine the velocity and acceleration of one particle with respect to another. In this problem, we're gonna use the planes as a particle. So we're gonna from the picture you can see that we're gonna compare two planes, and we're gonna find the velocity and acceleration of one plane with respect to another. So let's go and see the problem. So the problem has two parts. The first part, the problem says two planes are flying in a straight line path, maintaining the same altitude. The angle between the straight line path is 45 degree. The constant velocity so what it tells us that this plane A is moving in this direction at 500 kilometer per hour, and this plane 700 kilometer per hour in this direction, and then the angle is 45 degree. So this angle is 45 degree. The constant velocity are given, so they want to determine the velocity of plane B with respect to. So they want velocity of plane B with respect to A. They want us to find that. On the second part, it says if the plane starts to decelerate. So if plane A, so if this plane A starts to decelerate, so opposite of acceleration, at that direction of 50 kilometer per hour, while the plane B is changing its course. So that was the previous course of the plane B. Now it's changing its course to a circular path after a while. So maybe after a while, it's changing this course to in this direction, and it has acceleration of 100 kilometer per hour square, and the radius of curvature of this path is 100 kilometer. So, and this part wants us to find what is the acceleration of plane B with respect to A. So this is the question. Now let's go and start solving the problem. So let's first start with the part A. So part A, where we're gonna find only the velocity. So let's find what is given. So given is the velocity A, which is in this direction of plane, this direction, which is given as a 500 kilometer per hour. The velocity v is also given which is 700 kilometer per hour, which is in different direction. So this direction, it's a different plane, so it is A and this is B, and this angle is 45. So angle theta is also given, which is 45 degree. So these things are given. Let's move what's unknown. So first, for the first problem, the unknown is velocity v, velocity of B with respect to A. So how the plane A will see the velocity, the relative velocity of B from A. So how the plane A will see the velocity of B, relative velocity of B. So let's start our solution. We know first solution for relative motion, we know that we can apply the vector rule. If we can extend this line this direction, so it'll be VA and VB, and when you have to find VB with respect to A, so the arrow is going, so when you're finding B with respect to A, so the first B point, the arrow would be directing to the velocity B, and the last point A will be the start point of that arrow. So we're trying to find this this velocity with respect to this velocity, which is V with respect to VB with respect to A. So let's write our equation, which is VB equals to VA plus VB over A. So VA and VB, and we're looking for V over A. So VB equals to VA, VB equals to VA plus VBA. Now we see the coordinate system. It will be easier if we assume this is our x-axis and this is our y-axis, right? So now we have to take component to plug these values. So for VB, for this one, if this angle is 45, we can get the components VB sine, so this is also 45 because it's opposite, so VB sine 45, which will give us the I component, plus VB cos 45, which will give us the J component. So cos 45 will give us this J component, and on the other side we have VA, which is already traveling in this in this direction, so it's already on J axis but in negative side, so we're gonna put negative 500J, and we have the things that we need to find, the B with respect to A. Now if we solve, we plug value VB equals to 700 and 700. Sin 45 and cos 45 in this case would be same, which is 1 over root 2. So if we solve, if we solve, then we get VB with respect to A equals to 494.97 in I direction plus 994.97 in J direction. So this will be our vector form. So this will be our velocity in vector form. Let's find the magnitude, the angle of this relative velocity. So let's move to the next slide. So the velocity VB with respect to A, the magnitude would be the square root of 494.97 whole square plus the 994.97 whole square. That will give us 1111.29 kilometer per hour. So this is our magnitude, our answer, and then the direction we can find tan inverse. So you know the y component 994.97 over x component 494.97, which will give us 63.55 degree. So this will be our angle. So how do we represent that? So since our x component and y component both were positive, so we'll have x component in this direction, which is 494.97, and y component is in y direction, which is also positive, 994.97. Now we have the relative velocity v over a, and then the angle is 63.55 degree. So this is our first part of the problem. Let's move to the second part of the problem, where we're gonna solve for acceleration. So next, move to the next slide, part B, where we're going to solve for acceleration. So in this case, the given are the acceleration a which is decelerating, so negative. So let's draw the plane. It will be easier. So the plane was moving this direction. So since it's decelerating, so the deceleration would be in opposite direction, which is positive. So in this case, we're not gonna put negative, we're gonna put positive 50 kilometer per hour square. Acceleration of B is also given, which is 100 kilometer per hour square, which was moving in this direction, and the angle between these two is 45. Okay, so A, B, acceleration of B and acceleration of A, and it has a curved path. So here it will have a curve which has a radius of curvature 100 kilometer. 100 kilometer radius of curvature. It's moving in this direction, so the plane is accelerating in this direction. So now the plane is here at that point. It starts to accelerating in circular path. To solve this problem, we know that if it's a plane is moving in a circular direction, we will have a normal component. So okay, before that, let's find what is unknowns. Unknowns is the acceleration of B with respect to A. Okay, so now we have our given and unknowns. Now I start solution. So like we were saying, when a plane is having a curved path, circular curved path with the radius of curvature given, so we need to find so the acceleration will have a normal component. So I'm gonna draw this part separate here. So if we assume this is the vertical line, so if we draw it again, vertical line, it will have a tangential component of the acceleration which is along tangent, so it will be along the same direction it was traveling, 45 degree, and now it will have a normal component because of the curvature path. So normal component would be 90 degree of that path, so it would be the normal component. So A, B, normal component, and this will be our A, B, tangential component. So now let's find what is the normal component. A, B, normal component. How to find that? If we have the velocity v whole square over rho, which is the radius of curvature, so we'll get 700 over 100. Radius of curvature is whole square, so we'll get 4900 kilometer per hour. Kilometer per hour square. So we have to use that radius of curvature. So that we just find is radius of curvature, normal component of the acceleration, 4900 kilometer per hour square. And for the solution, we know continuation of from previous slide. We know for velocity, acceleration B is equals to acceleration A plus the acceleration B with respect to A. And now let me draw that again. We have this acceleration which is 45 degree, and we have the normal component which is 90 degree from here, so that is the normal component, and this is the tangential component of acceleration B. So to solve this problem, we again need the x and y coordinate system, which is easier to solve. So for this part, this tangential component will have an x and y component, and also for the normal component of the acceleration will again have a x and y. Since this is 45, this is 45, and this is 90, so this will again gonna be 45 degree. So now let's solve, write the equation. we will have AB tangential, which is sine 45. It will be in I direction, plus AB tangential component cos 45 degree in J direction. So both are positive because we're working on this part. So both component x and y is in positive direction. So both are positive. Now for the normal component, we will have positive AB normal sine 45 degree, I negative, we mark that this is negative, or we're gonna say y negative AB normal cos 45 J. This is the one side, and this is only the B part, acceleration B components. This is because when we take component of the normal part, this and this direction, the cos J part is in negative direction, so it is negative, but the I component is in this direction, which is positive. So we'll have J component, and on the other side we know the plane A is decelerating on the J direction, so we don't have to worry about that. It's decelerating, so it's positive, which is positive 50. So we'll write that on this side 50 J positive, and then our unknown, which is A B with respect to A. So if we solve this, if we plug the value, we know what AB is. AB tangential component, this value we just found, it is 4990, and this tangential component is the same, and that is given, which is 100 km/h square, and we know the angle cos 45 and sin 45, which are 1/√2. We found this, so we just only unknown is this one, and we can solve this. So if we solve, we get A B over A becomes 3535.54 I negative 3444.12 J. So this is the vector form of the relative acceleration. So now we can find the angle and magnitude. So to find the magnitude, A B over A gives us, taking the square root of 3535.54 whole square plus 3444.12 whole square, which will give us 4885.44 km/h square. And if we do the angle, theta equals to tan inverse 3 4 for the y component, 1 2 and 3535.54. If we do this, we'll get theta equals to 44.24 degree. So this is our angle, and this is the magnitude. One thing to notice is that we have not put the negative sign here when we were calculating the angle. This is not needed because when we gonna show the direction 44, because we use the y component positive part in this direction. So that's how we're going to show it. 3535.54, and we're going to put this as negative 3444.12. So now when we apply trig, we find the angle 44.24. So that's how we do not need to put a negative on the equation here. We don't need it. We just show that the direction is in this direction, and the angle is 44.24. So this is our acceleration, relative acceleration. So we have solved the problem. We're gonna move to chapter 13 and start solving, deriving theory and solve some examples. Till then, thank you. See you. Bye.